What is happening, physical science people? Today is Mole Day, or it was Mole Day when we first introduced this, and for you now it's just virtually Mole Day. You have been taught something without knowing that you've been taught something, right? I call that being Mr. Miyagi for you Karate Kid fans. I want to teach you what a mole is today, okay? When you hear the word mole, you might think of something like the animal, right? Or the very bizarre star-faced mole. That one freaks me out still. That's kind of Stranger Things-esque, isn't it? Or a mole on a person's face, okay? But that's not what I'm talking about. When I talk about a mole, I'm talking about something else. It's like a chemist's dozen donuts. Here's what I mean. When I was in kindergarten, I was sitting there in a class and the teacher was asking the students, how much is a dozen? And everybody was raising their hands and they were throwing answers. They're like 100, 1,000,000, 1,000. And I was like, have you kids never been to get donuts? So I sat there with my hand up, just waiting to be called on. And then I said, it's 12, right? Because I had had donuts. I love donuts. 1 dozen is 12 donuts, right? So it allows us to talk about donuts in different quantities. Instead of having to count every individual donut, you can count the donuts by dozens. So 100 dozen donuts is actually 100 times 12. It's 1,200 donuts, right? And it'll also give you diabetes. So a dozen is how we count individual donuts without having to count each individual donut. We count them by dozens, right? That's exactly what a mole is like, except a mole is a huge, huge number, okay? 6.02 times 10 to the 23. What this means is that the decimal place is really moved over to the right 23 spots. And if there's not a number there, then you add a 0. And that's a lot of zeros. So this is 1 mole. I don't think there's been that many donuts made ever in the history of the earth. That's a huge number. Now, why would we use such a huge number? In chemistry, nobody is doing chemistry with 1 or 2 atoms, right? Nobody's using 1 salt molecule, right? Or 1 water molecule, or even a handful of them. We're using billions upon billions upon billions of these molecules, right? So we can't talk about chemistry, actual chemistry, as if we're using individual atoms. We have to talk about it in moles, much larger quantities. And when it comes to atoms, this is not an unreasonable number because it takes so many atoms before we can actually interact with them because they're so small, right? That's a lot of donuts. So a mole has a nickname. That number is called Avogadro's number. Avogadro is just another old dead scientist. Here's his full name, Lorenzo Romano Amedeo Carlo Avogadro de Quarenga e di Caretto. I know I butchered that, right? But goodness gracious, who needs that many names, right? Cher only had 1. Give me a break. This was an Italian scientist. Looks like a real fun guy, right? Maybe he had a mole too. He came up with this number, and we call it Avogadro's number when we're trying to describe large amounts of atoms, okay? Now, for example, here's 1 water molecule. There's no way that we're ever going to do chemistry with 1 or 2 water molecules. We're talking about billions of water molecules, right? So if you took a mole of water molecules, remember that 6.02 times 10 to the 23rd, that huge number, right? It would be a manageable amount of water, right? You could fit it in a graduated cylinder. You've worked with a mole of water before. Maybe you've already had a drink today that consisted of way more than 1 mole of water, right? How about sugar? If you get 342.3 grams of sugar, okay, that's 1 mole of sugar. Here is sucrose up here, H22O11. If you gather 12 carbons, 22 hydrogens, and 11 oxygens, okay, that's not very many atoms. But if you get a mole of this molecule, 6.02 times 10 to the 23rd sugar molecules, then you'll have 342.3 grams. You could fit that on a scale. That's less than a pound, right? Normally, sugar comes in the store packed in 4-pound packages. That's way more than 1 mole of sugar. But at least we can see it now. At least we can measure it. At least we can interact with it. This is how chemists do science. A mole of salt If you measure out 58.4 grams of NaCl, it's a pretty small pile, but that is 1 mole of salt. On another day, we'll teach you how we came up with these numbers. But just know that nobody's doing chemistry with 1 salt molecule. We have to do our chemistry with moles of salt molecules, right? So why use the mole? Well, if we balance this equation, which you are now a little bit more familiar with, you can see that on this side of the equation we have 2 nitrogen, on this side we have 2 nitrogen, right? On this side of the equation we have 2 oxygen, and over here we have 5 oxygen, so we have to balance it. We've taught you to put coefficients, right? Whole numbers over here in these spots to try and balance them out. But guess what, ladies and gentlemen? Guess what those coefficients actually represent? Do you know what those whole numbers are that you've actually been putting in front of these chemical equations? They are actually moles. You've been learning how to use moles all along. We just didn't tell you what a mole was yet until this very moment. Those are moles. So as you balance an equation, as you learn that skill, you're actually already figuring out how much of each molecule is needed in order to do this chemistry in the real world, because nobody's dealing with 2 nitrogen atoms. Give me a break. Nobody's dealing with 2 oxygen atoms. They're too small. We have to deal with these in 6.02 times 10 to the 23rd, right? We have to use moles. So the ratios, whether you're talking about small atoms or huge collections of atoms, the ratios are exactly the same. So more on this today. Or on another day, we want you to understand what a mole is and that those numbers that you're using to balance equations are actually moles. Please ask questions if that didn't make any sense.